So why is undergraduate research such an important part of a university's mission?
Well, so we do it around here because over the years we've noticed this transformation in our students. They come in thinking of themselves as likely to be a cog in a machine for the rest of their life. And over again they come out thinking of themselves as someone who could design that machine. That it expands how a student thinks about themselves and what they are capable of. And in the end, that's what I think we're supposed to be doing at the university level. You know, in my classes, they're learning specific skills and ways to do specific calculations, but in one of these projects, which are open-ended, they have to bring themselves to it. I don't stand over their shoulder telling them what to do and when it's due and you know what check boxes they have to follow. They have to bring a level of creativity and self-motivation to it, and it's the kind of skill that employers are looking for. And our students are going on and they're getting jobs at places like SpaceX and NASA and Oak Ridge National Laboratories. In part because they're already awesome, and in part because they've had this experience that allows them this flexible and creative outlet to do something new and original and think through how they're going to conduct themselves over their career as researchers and scientists rather than just how they're going to be students. It's a lot of extra work, both on our part and on the students' part, but the experience is transformative and I think makes them who they actually want to be.
So on this first one, we've done a lot of stuff to move things, and then Acer and Eric added the sun to this model, and we're at the point where we've got most of the stuff done. We're just trying to write it up and get it pushed out the door on that one. So that was pretty mature. We just need some good writers, which we're going to start doing that. The second one, our model, we have a lady in Serbia who's looking at her model, and she's got the paper like 3/4 written, but she's got some health issues, so she's kind of been in and out. And she was trying to write something up to show that our model works as good as everybody else's model. And so that was, we're just kind of waiting on her.
Is this the one with Amy Barr?
Yeah.
Oh, she already didn't get on here. But
No, sorry.
Is that later?
Yeah.
Oh, okay.
Which one am I talking about?
I think she does.
The
second an outside collaboration.
Yeah. She works for the Planetary Institute. Optimal structure. This one, I've got a group of 4 students working on this project where we're going to try to build a big tower and then minimize it, doing some like Monte Carlo methods on it. See it? I've already got 4 students on that one. Fireballs one is Dr. Hibbs' project, and what he does is we got all these asteroids hitting the Earth, not hitting the Earth, but burning up in the atmosphere, and you'll see a streak. Holler if I do something wrong. You'll see a streak, and they supposedly took these streaks and mapped the streaks out, and then they can figure out what the projectile, what the direction is coming at, and then back it off, and you'll get an ellipse from where that is going around the sun. And they've got like 5,000 data points. Now the sun's here. If it's spinning like this, we're going around like this. And then you got the asteroid belt. The asteroid belt's pretty skinny. If these things come from the asteroid belt, these angles should be a pretty steep angle, I mean, pretty shallow angle coming in. But they think a lot of them are coming in from steep angles. If they're coming in from steep angles, they ain't coming in from the asteroid belt. So where are they coming in from? And so he's got like 5,000 data points. So we're going to take these 5,000 data points and try to graphically draw all these ellipses and see are the places where they're clustering, not from where we think they are. And that'll be some pretty neat stuff. Kind of give the general overview on that one. So he's got the data, and Dr. Cook, that's Cook, this is Cox. Cook's is probably going to be working on that one. He's got a student already kind of lined up.
Dr. Cox, we worked
Cox.
That one.
I got you. The binary star stuff, that's kind of mature. We've worked on that for several years, but Dr. Garrity wants to keep working on it. Ed's actually got it written up, but Dr. Garrity wants to do some more stuff. That's got like 5,000-10,000 lines of code in it.
That's what I do.
So it's a kind of mature one. But Ed's still around and worked on that project a lot. So if you want to start working on that one, then we could fit you into that project too. But that's got a lot of code already done.
It's sort of a thing that's coming up here. But if you think yourself not as someone who wants to do like really hard research, but you would like to instead take these projects that have been worked on and write them up into a paper form, we have a lot of need for that as well. So I feel like that's more to your strength. There's a place for you, very much.
So I talked to Ed about the binary star. That's working with Dr. Gary in physics. This one, Dr. Brady from the Agriculture Extension Center out on 281. What they would like to do when, like in Houston got flooded, you don't know if you got contaminated water or not. And so they have to send a team, and it might take a week or two to get your team and all that in there to do samples on your water. So what he would like to do is send out a little sample thing. So it's kind of this citizen scientist stuff. Send out this water sample, and what you do, it'll already be seeded with these
catalysts,
something reactors. If it's got E. coli 247, this one will glow. And if it's got Salmonella 273, this one will glow. And so it's already filled up, mail them out, they pour water on it, it glows certain colors, and you take a picture of it and you send it back in to the lab, wherever the lab's at, and they can analyze it. So that way, when Houston got flooded, you mail out all these things, you got all these citizen scientists going all over Houston, checking their water, and they can figure out what you have, where you have it, and what you need to do. Maybe you don't need to do anything. Or you're a farmer and you're putting you're watering your crops. There's a certain type of E. coli that cattle have that kills us. And there's a lot of E. coli that doesn't matter. And it'd be nice if they could check their water samples every time before they water their plants to see if this is going to make spinach deadly or not. It's kind of like when Japan, when the reactors exploded in Japan, the scientists thought it was going to go out in a certain area that was going to be dangerous. So some people figured out how to make a really quick, cheap Geiger counter, and they sent that out to everybody, and people just started walking around the street with a Geiger counter, and then sending the information back, and they found out that the dangerous part, the cloud that went through, went in a way different direction than scientists thought it was going to do, but it's done by citizens. And this is the same kind of idea, and that's a big deal out there now.
The big mathematics behind this is an attempt to take what's already been produced and redesign it to make it far more efficient to be able to detect for more contaminants in more cheaply and in a better fashion. So a lot of this is combinatorial, kind of geometric layout stuff with a sort of design and experiment layer on top of it, how we detect 4 different things in different places in the most efficient fashion.
But since a little coop like this, it may have 300 holes in it, but they'd like to fit as many, maybe check for 1,000 different types of viruses or bacteria inside this. So it's a way you can cluster these in a better way to pack it tighter.
Okay. We have to go even faster now, but we're going to pause. We're going to skip through to page, I guess, 3 now, so that one of our guests can talk about her thing. So we're at the bottom here, the EEG statistical analysis process refinement. This is Dr. Amber Moser from your affiliation. Knock it up.
Yeah, so I'm an assistant professor in psychological sciences and a faculty research fellow in the Office of Research and Innovation. I'm a neuroscientist working in cellular electrophysiology. We have 2 electroencephalograms on the 2nd floor. We record brain activity from individuals who have chronic pain and or who use opiate-based drugs for treatment or cannabinoids like marijuana. We're recording those differences. The EEG software gives us those data as amplitude over time, and we do some transformations to switch it to frequency over time so we can get meaning from our cellular data. We also filter our data and do some artifact rejection analyses. So I'm interested in working with a couple of graduate students on projects along those lines. I think I might have sucked these 2 guys over here. I'm not sure, but anyway, let me know. I have 10 or 12 research projects going at any time, so there's lots of blood to go around. Thanks for having me.
The main need here is not so much mathematical modeling, but it's statistical analysis here, right? And visualization. Or is there also mathematical modeling behind it as well?
All of it.
Okay.
All of it.
All
Yeah.
of it.
Yeah.
Cool.
Mm-hmm. Thank you.
Thank you, Dr.
Thanks
Moser.
for the pizza.
Anytime. Okay. Can I do some more?
Sure.
All right, we'll come back to page 2. We'll actually knock out the rest of the page that Dr. Moser was just on. So we'll go to the top. So these are some of my projects. This is a brand new project. On the page before it, I will talk to you about gerrymandering. This is a spin-off of the gerrymandering project. But the basic idea is to take the way land. Is there a typo? No. Okay. To take the way land is currently being split up into either school district pieces or political voting districts, but see how land is being split up and see if it's fair or not in some sense, and then try to wiggle where those boundary lines are to make it more fair. In this case, it's the idea to take the way that Erath County is split up into school districts, see if you can move those boundaries around to make sure that the districts are funded at more equitable levels. So it's to equalize the funding levels amongst all school districts. And then to apply the idea more broadly throughout Texas and outside. This is much like gerrymandering from that said. This is brand new, it's with Ann Hamilton, the Political Science Department, and right now Sabrina has still been working on it, but if anyone else is interested, there's room for it. Whereas Baron-Trawl, this one's probably more or less closed at this point, but I'm meeting with Dr. Bell next week. This was some statistical analysis on the level of this particular chemical within different species of grapes, but that one may be done. The Hadoop cluster. One of the cool things this last summer is our esteemed President Ed Smith and Tim Nguyen hung out with me for the summer, and we set up what's called a Hadoop cluster. This is your state-of-the-art for managing gigantic data sets. Think of your biggest data set that you know, and then think of another one, and another one, and another one, and put them all together, and then do that 9,000 more times, and you'll have the right scale of the data set we're talking about here. Hadoop does this by taking a bunch of machines and cobbling them together so that when one fails, you can rebuild the data that that one had based upon what all the other ones knew. So it's redundant, and we did this with 6 computers that were being thrown away from the IT department.
Another thing on Hadoop, your resume would look really good if you got Hadoop cluster stuff on your resume, because they're looking for that kind of stuff.
Let me give you a few names of companies that rest on Hadoop. Amazon, Alibaba, Facebook, Twitter. I could go on for a really, really long time. I think SpaceX uses it. Basically everyone who has big, big data sets and is cutting edge, they're working on Hadoop, and this is one of the things that people really want. Right now, the project at Stanford is largely mature because NN2 got it set up in about a week, and I thought I'd take them all summer. So, but there is going to be probably more requests from around the campus to take big data sets that are laying around in people's hard drives and consolidating them into this one centralized location. So if you're interested in doing that kind of work, that is likely what will happen with Hadoop cluster. C-phages. So this is joint with Dustin Edwards in biology, and Smith is already working on it. You haven't already heard about C-phages. It's a big thing going on over in their department. But the idea is there are these viruses that attack by bacteria, and genetically this is incredibly interesting. It holds the potential for cures of all sorts, improved manufacturing processes of all sorts, and they are in the business of analyzing genetic information from those bacteriophages and trying to make sense out of them. Anything to add on that one, Ed?
The biggest thing we're just looking at clustering and some regression stuff on some things.
So mathematically, we're doing what's called clustering analysis and some regression analysis, but within the broader scope of the project, there's a myriad ways you can get involved if you're interested.
And this is going to really grow to think of where bacteria are getting become antibiotic resistant. Well, this is a complete new thing. In a handful of dirt, there's trillions of different kinds of viruses in one handful of dirt. And viruses, if you put a virus in, viruses are real specific. You know, if I give you a virus, it won't hurt you at all, but it may kill this bacteria. So it's not dangerous. If I find a virus that kills a certain bacteria, what they do is they're trying to isolate that, put it in a capsule, get you to take it.
And there's, I think there's 3 already in there, 3 projects you can get out of there.
At least, so yeah, there's
a lot there.
The Putnam exam. Putnam exam is an incredibly hard math exam. Very, 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 very hard. The median score across the nation is a 0. So, if you like trying to do really hard things and know that if you fail, you're like everybody else, this would be a good thing to get involved in. I took it, and the max score is like a 120, and I think I got a 6 when I was undergraduate. So that's the scale you're looking for. It's just if you want to think about something way harder than you've dealt with before, and see if you can make any progress on it. If you fail, no one cares. If you succeed, everyone cares. So that's a win-win, right? Jared Domine and Nicholas Patella are planning to do it. It happens on December 1st, and they're basically going to study to crack it at least to some extent. This project, Optimizing Science Funding. This one is relatively mature. This was worked on by Clayton Boone, Pedro Romero, and Tu Nguyen under me last year. The idea is there's a big website called the Archive where scientists post their papers before they go into traditional journals. We wanted to take all that data and figure out which fields of science have the most influence on which other fields of science, based upon co-authorships on scientific papers, and then turn that information in a way to attempt to say how to optimally distribute limited funding to get the most science out of things. And so that's got some work here, but I think a lot of this would be writing up what's already been done. There's some low-hanging fruit here for turning into a paper. And we did EEG stuff. So there's page 3. Let's flip back to page 2 and let Wyatt talk for a while. On the back of the first page, sorry, the back of the first page now.
This was just, I was just thought of this one. If we have anybody that's artistically, if you know, somebody who's kind of decided if they want to be a math major or not, and they got artistic, you know, spin to them. There's a lot of neat stuff you can do with fractals. It makes them really pretty art and that kind of stuff. I just had a girl last year that was, she was an art major, and I had her in Cal 2, and I wondered, why the hell are you in Cal 2? But I thought that was kind of neat. If I'd had something like this going, I might could have hooked her in and got her to maybe change to a math major and do her art with that kind of stuff. So it's just some cool stuff. If you know anybody or any of y'all want to do some cool stuff with fractals and make some art out of it, I thought that might be a neat project for somebody that was artistically inclined. Oh, this one was a pretty neat project we did last year. It's got a lot more work to do on it. They had some really good results at the end of the year. We got it where it works really good. The travel center works really good with smaller sets. All the ideas should extend into bigger sets, but we're having some problems with, you know, the densities getting too big and it's blowing the walls off and stuff like that. What we do, the travel salesman problem, you've got a salesman has, you know, 5 cities he's got to go to. Well, I'm starting at Stevensville, I got 4 other cities that I go to. How many choices I got? 4. Once I make a choice, how many choices I got? 3. Once I make another choice, how many choices I got? 2. And so it's 4 factorial. And if I go backwards or forwards, it's the same thing. So 4 factorial is 24. Backwards or forwards, cut it in half. So it's 24 choices if I got 5 cities. So you do your 12 deals, figure out which one's the smallest, and that's the route I should take. It's pretty simple, right? Maybe bank that up to maybe you got 25 cities you got to visit. So that's not unrealistic to have 25 cities that on your route. Well, how many choices are there? There's, I think it's 1 billion trillion choices with just 25 cities. And we figured out if you had a supercomputer that started 4.5 million years ago and did 1 billion calculations every second, it would just finish today. So 1 billion calculations every second for 4.5 million years, you can finish that problem. Okay, so you can't do that. So what we did, we turned it into an antibody problem, and then we did a bunch of crap, and we got some really good answers. But extending it out to bigger problems, we're having a little bit of problem. It looks like it should, whatever the word I'm looking for, scale to bigger problems. But that's where we're at now. And then Ed and Steph and Ed, I just said Ed Wynn, another Ed, have graduated, so it's kind of open, but you can be jumping into the middle of the project.
Yeah, well, it's kind of undershot this one too as well. They got some good results. They won the first prize at the big statewide competition last year. So.
And it's a big math. If you get a really good solution to the travel salesman problem, you're a big
Amazon will
math.
hire you instantaneously.
Yeah, and there's a lot of problems out there that here's a data set and here's the best answers. One that's got, I forgot what it's called, but if you get a better answer that's out there, they give you $1,000. And it's just sitting there, but it's got 100,000 nodes, so it's kind of
yeah. All right, cool. Gerrymandering, that's just a second ago. This, you heard the word gerrymandering in the news constantly. There's all kinds of legal cases around it. It's the idea that political boundaries have been drawn unfairly to advantage one group and disadvantage another group. And it's illegal, but it's really, really hard to detect and really, really hard to prove unless you're a mathematician. That's where mathematics comes in. It's how the mathematics is the study of measuring hard to measure things. And gerrymanderers in the process, or this gerrymandering group in the process of trying to help improve mathematical tools to fight that. We'll hear more about that in here 1 week from today. Ramsey numbers. For the sake of time, I'm not going to get into what a Ramsey number is. It is a combinatorial number that is important if you are designing computer networks. And they are very, very hard to track down. The best you usually do is say that it is between here and here. We would like to make it be between here and here, or between here and here. This is a process of improving bounds on the how big and how small these Ramsey numbers are. This is a parallel processing using the GPU upstairs. Nicholas Patel, Jared Dominic, and Mason McCallum are working on it. If you're interested, it's in midlife, but we made some real progress over the summer. The magic snake. Nicholas Patella, show us a magic snake.
So basically, it's actually a Rubik's snake. Our Rubik's snake guy who made the Rubik's Cube made this little twisty thing, and you can make it into all sorts of different configurations. The box that I got my first one off of said it offers endless possibilities. As mathematicians, we know this is wrong. So it's basically using combinatorics to count them, and this actually connects to a surprising number of open problems that this is just really, really adjacent to. Which, so even if you think, well, this is just a toy problem, it actually is kind of relevant to some other stuff.
No, the sentence wrong. It's a toy problem.
Yeah, it's a toy problem.
Right? It's a problem to play with toys, but there's real math behind it.
Yeah.
UN Climate Change Networking. This is joined with Anna from the Political Science Department. The United Nations publishes a gigantic database of people involved in grants to try to achieve sustainable development throughout the world. The question is, what does that network look like? Do people interact with each other, interact with each other a lot, or is it very Spartan and very removed and very disjoint? This is an attempt to take that database and answer the questions, how do you get these sort of regimes to form? It's very political science oriented. If that appeals to you, this could be a good project. Nguyen has been working on it for a while, so it's in midlife. They call it midlife for sure. Yeah, midlife, that's pretty reasonable, I think. Do anything, is that midlife? Okay, last page. Yep. Dr. Cox, I think it's almost your turn. Come on up.
All right.
Flooding app development. This is also with the Political Science Department. When Hurricane Harvey happened, people knew where the flooding was going to happen, but the people who were in the flooding zones did not. There are very nice models for predicting that. The goal of this is fairly simple, to be able to tell people who are about to be flooded that they are about to be flooded, by way of designing some kind of an app that would allow us to communicate that alert information more effectively than what is out there right now.
Hi, so I have a couple of problems. They're all new problems. I'm new here, and they're related to billiard dynamics. And the idea of billiard dynamics is just what you expect. You're thinking of like when you play billiards on a pool table and bounce your billiard ball around, except in our case, we're assuming there's no friction. So we're interested in what happens as you just let it go forever and it just keeps bouncing and bouncing. And there's all sorts of applications of these problems, and they've been studied for about 50 years. And the way we kind of look at it when we're studying these problems is that what can happen depends on your choice of a table here, a billiard table, and if it's very structured, like for example, just a rectangle or a circle, you get this very regular behavior. But on the other hand, some of the biggest advances, like this is the Bunamovich Stadium here, was when people realized you could get chaotic behavior if you had certain types of tables there. So this is kind of the emphasis that you want to look at when we're studying billiard dynamics, is that when you get this very regular where all that worked so far was with billiards with no English on the billiards. You weren't allowed to spin. But we're working with a model here where you allow spin on it, and all these same sort of questions are still out there, but no one's looked at this yet, so there's just all sorts of open questions. And I chose two here on the list, which are ones that if you're willing to do a little bit of coding and a little bit of numerical simulation, you can come up and answer these questions that no one knows right now. And so that's one project. On the other hand, it's not known yet that there are any completely chaotic, in a specific sense, ergodic ones for no-slip billiards. Now there's evidence that there is some chaos, and for that we look at what's called the phase space, which is just looking at the trajectories, but looking at what's going on with the velocities, how that changed. And looking at some of these, there's evidence going from left to right there that you can create chaos. You know, the ones with these circles there are the ones where it's really structured. The chaotic ones is where it's just bouncing around randomly, like, static on your TV. And just looking at the phase portraits, it looks like that this is the case, but so far there's zero quantitative evidence that you can get any chaos in this. But that's basically because no one has checked. There's something called the Lyapunov exponents. We know how to program simulations for these. And so that's what the second project is. If you're interested in looking at some Lyapunov exponents, you might find the first evidence of chaos in no-slip billiards. Oh, and so I have a few sheets up here. If you want to see more details, feel free to pick one up, or just email me and I can send it to you.
And since Dr. Cox is new, you may not know where he lives, but if you know where I live, he is next door to me. So he's right down the first floor, right next door. These last two, 1 minute wide.
This one, Travis worked on this one a while, and this one, we're working with a guy from Harvard for a while.
Okay, that's good.
We're just trying to see how, they're trying to see how stuff self-assembles and makes different shapes. Travis worked on it for a while, and it's got a lot of code that's already written, so if you want to, that one, I thought it was a neat project. We never wrote it up, but we got.
Other walking up here. This one is another political scientist, Deborah Lyles. She's new to campus. She has this interesting data about how slave ownership and livestock production changed during pre-Civil War era, and she uses it visualized. She has a very nice template for what she wants to have it look like. This one is pretty much ready to go if you want to do any kind of like fairly low-level statistics and visualization, and you are interested in political science and history, that kind of thing.
We also have a couple of math education research projects that are going on. Dr. Smith has several where she's working with looking at communication and ways students are communicating. I'm working with a couple of graduate students who are looking at classroom practices and their impact on student achievement scores in developmental math. So if you are interested in math education research, please come see me or Dr. Smith.
So again, just to briefly recap, big moments of things, choose what kind of project you're interested in, and choose what you want to be doing. If you just want to write, we got work for that. If you want to code, we got work for that. If you want to think about games, and if you want to do like more pure math, we got stuff for that. But if you're going to do it, make sure you're committed and you really want to, because we don't have the time with this many people and this many projects to chase you. It's going to be up to you to make a success. We will help guide you, but it's going to be up to you to make it work.
And I might mention, Mr. Marwin's working on some robotics projects.
Oh,
There's a huge amount of mathematics in it, and if you're interested in the whole subject, what are kind of issues.
Two had a quick announcement on that. I'm sorry.
Things to work autonomously, and you know.
Yeah, so Steve, by the way,